Okay, Peter's last supper, so to speak, his last commentary was about sources of bias in AI systems. And today I want to talk about the human aspects of how do we build these things and what should we be thinking about? So I'm going to do a little bit of history. No, I'm going to do a lot of history in order to tell you a little story about how we got to where we are now. So remember this diagram? Once upon a time, there was machine learning, but that's a version of AI, which is situated within complex software systems. Now, we all live and work with complex systems that we do not really understand. I do not know how carburation in my car works. I have a kind of vague idea about how it works, but if something goes wrong, what do I do? Right? So let's talk about complex software systems because they're also part of our culture. Space travel, going to the moon, giant robots, giant spaceships that are intelligent. These are all part of what we think of as part of the way we think about AI. So this little section coming up is how do we think about AI and how do we as a culture deal with it? So if you haven't seen 2001: A Space Odyssey, which I realize is a date before many of you were born, but for us, for Peter and I at least, and for the DCI people in the room, it's the future, isn't it? I remember when I would say, oh, in 2001, we will have household robots or whatever, right? Because it was the indefinite future. I know it's the indefinite past for students, but anyway, this once upon a time was a vision. And there was a lot about that vision that was really interesting, including HAL 9000, the computer, which was built into the spaceship. Now, the plot, I will give you a little bit of a spoiler, but you got to get this in order to understand the story. This robot and this symbol, this computer, which ran all the environment and all of the systems, navigation, everything, did it all, like the Star Trek computer, right? It did it all. It kind of has a mental breakdown. And so the whole story is about how HAL does not do very well in the end. And so the humans and the AI systems are fighting. Is that a real concern that we should be thinking about? It's part of your culture. If somebody talks about the robot, the computer in HAL 9000 in 2001, they're talking about that. But the notion of computational devices built into our lives goes way back, way back. So the Antikythera device from roughly 100 BC was this amazing piece of machinery that was a calculator for astronomical events. So it could predict, for example, eclipses and different positions of stars in the sky. If you're an ancient Greek, this is AI to you. You turn a few dials and it would tell you there's going to be an eclipse tomorrow. Oh my gosh. Right. So that's the leading edge of technology at the time. There was also Heroes Cart, which is about, little 60 AD or so, which is a simple device. You could go build one now. And by setting pegs at various points, you could make it follow this little particular outline. Peter, you remember the Big Track? The little robot car thing, you can program it. It's the same thing 2,000 years later. So there are toys you can buy that will allow you to do the same thing now. But at the time, the context of history at the time, this device that would kind of wander around and do a pre-programmed path was just miraculous. So fast forward a couple centuries and we get things like Vaucanson's duck, which would quack like a duck, eat like a duck, and poop like a duck. So that diagram is actual the inners of it. Merlinger's dulcimer player, these are all automatons. So the interesting thing about these, or Manzetti's flute playing device, is that they were really pushing the boundaries of what behavior is. And people at the time said, oh, that's either very clever or you're a witch. You've imbued human behavior in mere metal and wood. So about this time, we start getting this notion of intelligence in devices, in systems. And the clever thing about, for example, the dulcimer player is there's a giant CAM network there. And it's basically, that's a program. It's telling it which string to strike and how to do it. It's basically a very fancy player piano. But in the 18th century, that was pure magic. More recently, we get robot stories in Blade Runner, or name your favorite thing, going back to 1950s with Forbidden Planet and the giant robot that appears there, or 1962, the Jetsons, Rosie the Robot, which was the robot that would do all your household tasks. Where's my household robot? Why haven't we achieved that? The answer to that is a really interesting answer. Turns out folding sheets, cleaning up messes is hard perceptually and hard robotically. It's a difficult task, much harder than you would think. And this, in some sense, is one of the fundamental lessons of AI. You think it's easy, it's not. Think it's easy, but it turns out to have a lot more complications than you would ever believe. 1965, Lost in Space, was constantly saying, "Danger, Will Robinson," and that's, I'm sure, what he's saying there. Again, these are just now part of the tropes of the way we think about AI systems. Peter has this picture of the Legend of Talos from 700 BC about basically golem-like giant animated things. And the word robot means worker in Hungarian. It comes from this play, RUL, Rossum's Universal Robots, in 1920. So the notion of robot has been actually in our language since then. Before that, they were automata. After that, they became basically servants, serfs kinds of things. And of course, nobody in my field, I'm sure, and Peter would say the same thing, was left uninfluenced by the talking computer built into the ship of Star Trek. We would all say at some point, our friend Amit was definitely moved to be building systems that could do something like that. And that's how we get to these tropes of the evil robot, the evil diabolical robot that is ultimately going to try to destroy humans in both 2001 and in the Terminator series. Now, this has been around for a long time. This is, wait, how many of you have heard about Mechanical Turk? Heard that? Okay, how many of you use it in the context of Amazon? Right, well, there's the Amazon Mechanical Turk, which is taken off of this Mechanical Turk. This is the Mechanical Turk in the late 18th century, which is presented as a box. And there's so many stories and morals here. Presented as a box with some fancy fancy mechanical gizmos that will play a very competent game of chess. Purportedly, it beat Napoleon at chess, and that's saying something, right? But the reality is that that's actually the way it worked. Pay no attention to the man behind the curtain. That little guy, very small human being, was a really great chess player, and he snuck inside the box and then moved the levers to actually play the game of chess. And so he's got actually a manipulator and a display so you can see what the game board is like. Okay. One of the stories here is AI often has secret, magical, hidden mechanisms, right? This is, I mean, charlatanism has been with us since time began. I think now AI is not so much trying to hide behind the curtain as the stuff behind the curtain is immensely complicated. But we've always got these multiple levels of explanation. There's a chess player at the surface level, but there's also something going on inside the box. So that's what Mechanical Turk originally refers to. We've had multiple devices like Radio Rex, which did speech reco. And when you would say Rex, it would come out and bark at you. The reality is it had this fancy little tuning fork inside that when your voice actuated it by vibrating, it would actually run a little, connect with a little electromagnet, make it come out and do the whole mechanism. But it's not at all voice reco. It's amplitude reco. That's it. So if you clap your hands, it would come out and do the same thing. Then a little bit later, 1964, Joseph Weizenbaum, and we're going to come back to this, but Joseph Weizenbaum built a chatbot. This is 64. 64. Built a chatbot that would hold very plausible sounding conversations. there's an example of a transcript between Eliza and the human. And what's interesting about this is that people have this inherent need to make sense of a conversation. So they see this dialogue between them and the system, and they go, oh yeah, it totally gets me. Totally gets me. So the thing about Eliza is that it's actually a fairly simple trick. In my AI classes back in before 2000, I used to teach people how to do it. And here's some of the code, how it works. And I can show you actually in probably 30 minutes, everything you need to know about Eliza. And I would hand it out as an assignment. Okay, students, you have 2 weeks, go implement Eliza. Okay? And then come back to me with a transcript showing me that it works. I stopped that after a while because what happens is that people build the system themselves and they start using it and they forget that they made it. And they start getting involved and invested in the conversation with a system that they know doesn't actually understand them in a meaningful way. And so I would get these long transcripts, 10, 20, 30 pages of transcript of somebody, one of my students, talking with their Eliza. Note, their Eliza. They built it. And yet I learned way too much about my students. I learned about their boyfriends and their girlfriends, their families falling apart. It's like, oh, stop. But it's kind of it's a response that you cannot stop. Does this sound like anything today? Does this ring any bells? I want to bring up this word, pareidolia. Pareidolia is the inherent response that people have to signs, symbols, all kinds of phenomena that they think of as having some kind of human face. For example, does that look like a humanoid to you? It might. How about that? The face on Mars. People saw that early and thought, there are Martians, there's evidence, we have a face on Mars. People respond positively to teddy bears. There's a thing called the teddy bear effect. And anybody who's written a lot of code knows this effect. Because if you explain the problem in your code to the teddy bear, you suddenly understand what the problem is. Oh, the teddy bear added no value, aside from being a foil for you to talk to. It's a kind of pareidolia effect, right? Now, what's interesting is when people debug code, I remember sitting in my lab working away, and somebody comes up to me and says, hey, Dan, help me with this code. I can't figure out, and they go on and on and on. I don't understand what they're saying. I have no idea what they're saying. Something about stack frames and pointer buffer overflows, and they go, oh, that's it. Thank you. Thank you, Dan. You helped me debug the problem. I was the teddy bear. Right. So this kind of effect is really striking. And Alan Turing said, you know, it's best if you can make someone fall in love with these systems because, oh, then we got a movie like this. How many people have seen Her? Just curious. Okay, wow, the rest of you, you have an assignment this weekend. Go watch Her. And the reason is that it's interesting use of chatbots. So Samantha, in this case, is the embodied, the invoiced Scarlett Johansson's voice, pretending to be a chatbot, which works really well, and this guy falls in love with it. And then things happen, shall we say, and I won't spoil it for you, but stuff happens. I will argue that's almost unavoidable. So it shouldn't surprise you to know that there are companies out there making their fortune, making their living by building chatbots that people fall in love with. There's a company called Replika.ai with a K, and their entire MO, modus operandi, is to build chatbots that embody, say, your dead father. Not Darth Vader, but some other dead father, right? Somebody else that you can then talk to and have relationships with. And they, interestingly, got into a bunch of, shall we say, user feedback, because there's a huge part of the community of Replika that had this very sort of erotic conversations with their replica. And when they turned that off or they turned it down, they got really unhappy, right? Because that's a service that you're no longer providing. And I thought I signed up for that. If you're interested, I'm not going to show it now, but this video showed how a chatbot could work back in 1987. So this is from Apple, and it's really worth watching because you can see when you watch it, you'll go, oh yeah, I've seen that before. I've seen that before. And it's basically a conversation between a kind of faculty member and an associate, and then the chatbot in the upper left corner with a little bow tie. You then see echoes of all of this in subsequent chatbots and subsequent search engines and so on. So it's a very fancy kind of Baroque laptop display you see there, but it's a really, really influential piece of video. I know multiple people in the Valley who were told, go implement Knowledge Navigator. That's your job. And I know multiple research teams, that's what they did for several years. Assignment, just a thought piece for you. Watch the video and say, how would I build that now? Could I build it now? Could it do all the things? So what I want to talk about for the rest of this lecture today and going into Thursdays are some of what I think of as the key issues about user interfaces, user experience, and AI. In particular, what are mental models? We're going to talk about mental models and what it means to design them. We'll talk about designer models, system models, and how all this plays together well or not well in practice. A couple of definitions. A mental model is how you think about it. Okay, what's my mental model of my car? You have one. You may not think about it that way, but a mental model is basically the way you think about a device or a system. So I did a lot of studies about how people thought about search, Google search. And I asked about 1,000 people this question: can you draw me a picture of how Google works? And this is an actual picture of what somebody drew. Did anything strike you about this picture? Yeah, they don't really have much of a model. They type something, magic happens, and it comes back, right? And so you see that box that says magic happens there? The surprising thing is basically a third of all the stack of 1,000 illustrations I have the word magic in them somewhere. 1/3. That means people really don't know what's going on. I type something and it comes back. That's not to say they don't have a mental model. They don't have a very deep mental model, right? So as a grad student, with all my copious spare time, one of the hobbies I had was learning how to pick locks. And in the process of learning how to pick locks, you have to develop a very deep mental model, a structural model of how the pins work and how the cylinder works and the shackle works, how all these things go together and what you have to do in order to defeat that. So you have to have a fairly deep and predictive model so you can know how to pick the lock. If I said, it's magic in there, I don't know if it's little gremlins or dwarves or elves. I don't know what's really happening, and it doesn't help me pick the lock. It doesn't give me any information. So Arthur C. Clarke, who wrote the book for 2001, said that any sufficiently advanced technology is indistinguishable from magic. And that's kind of true, But if you think about it, the contrapositive of that is any technology just distinguishable from magic is insufficiently advanced. That's sort of where we're at, right? So we have this relationship between magic, the sort of action and behavior without explanation, and the stuff that we're studying here in AI. So now you might say, oh, Dan, I am a rational human being. I don't believe in that stuff. Well, here's an upgrade that I got on my Mac a little while ago. And it gives me this display and it says restart is required. And it says, well, let me see, it gives you an explanation. And the explanation says it fixes an issue using certain character sequences that could cause apps to crash. I would like to know what those character sequences are. I would like to know what crashing means, So it doesn't really give me any explanation. Building a mental model is something we want to do. We as designers, we as AI system builders want our users to understand to first order how this thing works. Certain character sequences. That's the same as saying magical incantation. Right. So here's another one. It says here, important according to Google Magic. This is Google telling you that they have magic. Now, I don't think it's a good idea, but it's in the user interface. And so it totally matches your expectations, right? That's right. So I want to give you an interesting distinction here. This is from Don Norman, who says the way a designer thinks about a product that he or she is designing and building is fundamentally different than the user. This is something you should tattoo on your forehead. Designers are not users. System builders are not users. You need to understand the difference. The way you think about AI is not the way the user thinks about AI. There's a qualitative difference here. So the designer would say, well, I want it to be like this. I want it to have this particular affective response. I want it to work like this, blah, 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 right? The user's mental model, they don't know any of the backstory. They really don't. They don't know why you're doing this. They don't know who the stakeholders are. It's just that it's presented to them and they use it as given. So designers often expect the user mental model to be the same as theirs. Let me tell you, that's almost never true. There's a whole area of user experience research which seeks to understand and align what the designers think the users want and what the users actually think is happening. I spent 17 years at Google working on user experience research for search, which is an AI system. How do people understand it? Magic. Third of them think it's pure magic. So we all, like I said, we all have mental models, but they're often incomplete. They're often inaccurate. They're often non-predictive, and they don't like to be updated. People hate updating their mental models. So as system builders, designers, we need to think about how can we give people a functional mental model? It doesn't have to be mechanistic. Nobody wants to know about your precious network weights, right? They want to know what they can expect it to do. So, I need audio for this, so I'm going to change your settings, Peter. So type output, what HDMI? No, HDMI. Where's my HDMI? Is it this one? Oh, this one. Thank you. Thank you. That's it. Let's see if it works. Good. So this is, I think, a brilliant video that shows the distinction between the designer's mental model and the user's behavior. If you haven't watched it, no spoiler warnings, but it's worth the 2 minutes to watch.
How many times have you sat behind the mirror window with that pain expression on your face?
Excellent question, Peter. How many times have I sat behind the glass and watched the same thing happen? A lot, a lot. I ran a user experience lab at Apple, and we had one of these rooms where you would have a big pane of glass, and the users would come in and sit in front of the computer and do the thing. And we bring in the software engineers and designers, and you all sit and watch. My job was to prevent the engineers from pounding on the glass and saying, "Click in the upper right." I'm not joking. They would literally think, "Oh, those stupid users." I don't think that's the problem. The problem is really, how do we align the mental model of the user with the designer and the designer with the user? So in some sense, this is in fact the perfect video, because there's one solution that works. It's the minimum solution, lowest cost, most efficient, perfect. No thinking involved, just dump it in the square hole. Right? So I'm telling you this because we all have mental models, and perhaps you have a thermostat in your home, right? And thermostats classically work, they look like this one on the left. There's a little piece of mercury in a closed tube, and you set the arm depending on what temperature you want the furnace to come on or whatever. And so the key to making this work is that there's a bimetallic strip of metal that goes like this or like this, depending on it gets warm or cold. Very clever. So this is a brilliant device. Question for you, is it thinking? Let's leave that aside for a moment. But to what extent is this intelligent? Because it's responding based on temperature, ambient temperature, and then taking an action, right? So we can talk about that. One of the interesting pieces of work that's been done in mental models is on how people think about thermostats like this, okay? There are two models, one of which is that there's a feedback loop and another one which is a flow loop. And we won't go into the details of that, but let's explain that there are two ways of thinking about thermostats, okay? A very simple device. And so maybe you have done this. Have you ever set your thermostat to 90 degrees because you want the house to get warm faster? Anybody done that? Yeah, I know, the rest of you are lying. That's okay. We set it to 90 because I want it to be fast. I want it to get warm faster. But your mental model is busted because it's a binary device. All it does is it turns on the furnace or off the furnace. That's it. There's no flow rate. You can't turn it up to 90 and hope for it to get hotter faster. It will turn the furnace on, and if it, it does the best it can, but it doesn't go to 10% because you turned it to 60. Interestingly, the baseboard heaters actually do have a flow model. You can turn a baseboard heater to 50% and it will only go on to 50%. It won't go to 100. So this actually is the right mental model for baseboard heaters. They're like giant toasters. So what is a mental model? A mental model that you have determines what you think of as normal appearance and behavior, your mechanisms, your behaviors for using the system, how to fix it when things go wrong, and expectations about symbols and language of use. We can go on and on and on. And there have been multiple papers written explaining about what a mental model is, but this is in the end what a mental model is. So what this means is that your mental model gives you expectations about how to read, how to use, what the symbols are, how to fix things when things go wrong. So here, this is a real story. A friend of mine was making a white sauce, making it for like lasagna. And it was getting really thick, so keeps adding milk. And so he calls me up, says, "What's going wrong? Why is this not turning into my lovely bechamel sauce? What's wrong?" And this is on the phone, right? I don't know. How much flour did you use? Right? Because it's a milk flour sauce. How much flour did you use? And he says, it says to use 3 or 4 ounces, so use 3.5 ounces. I thought, wait, how much milk did you put in? And it was totally out of whack. I know how bechamel sauces work. What went wrong? When he read the recipe says to use 3 or 4 ounces of flour. And you can see the problem here. This is why it wasn't thinning out, because he had like a lot more flour. that he was supposed to have. So the mental model here was that if you write 3/4, you interpret that as 3 or 4, right? Not as 3/4. This problem of reading and symbol interpretation is going to come back to bite us multiple times. So this is actually a thermostat in my house. If you pull the cover off, it actually has that little mercury switch in it. Very cool. But it's got this whole thing in it, which has, you can set time of day to come on, off, blah, blah, blah. A bunch of stuff, right? One thing to notice here, if you look through this, it's got all these buttons and a lot of functionality. Notice this one right here. It says reset. It's a thermometer. It's a thermostat. Why do I need reset? Any ideas? Why do I need reset? Anybody? I'll tell you. Oh, yes. Yeah, go for it.
Software.
Correct. Absolutely correct. Because it's software, and software gets confused. And so power cycling a thermostat is a real pain. So they put a reset button on the thermostat. So this suggests that there's kind of a lot of complexity that may not be manageable. So let's think about this, because now we have AI-enabled thermostats like the Nest thermostat. Has a little ML model in there that understands when you come home, what temperature you would prefer, what the ambient temperature outside is. It takes all this into account. Okay? Are you okay with that? Now, what's your mental model of this thermostat? Probably don't know how it senses the temperature, but let's just assume there's some kind of digital readout, and it gives the system a number between 1 and say 200, and says that's the temperature. Now, here's the ugly reality of the Nest thermostat. It says, okay, if you want to restart your thermostat, it can resolve some issues like a frozen or slow display. Okay, this is an interesting design issue because all of a sudden you have slow thermostat displays. So the thing to notice here, at the very top, it says, when you restart your thermostat, it will not lose any of your information or settings if you restart it. This is like a computer. You restart your computer, fine, no problem. However, if you read carefully, which I predict less than half of the people will do, and you read the dark green here, resetting the network will remove all the network information from your thermostat. Oh. Do you know the difference between resetting your thermostat network and your thermostat per se? You see where I'm going with this? Communicating how the thing works, even for a device as simple as a thermostat, is hard. It's very hard. So when you're designing a product, especially one with AI in it, you need to figure out how to communicate a mental model that helps people figure out how this works and how to handle it when things go wrong. Restart versus reset. Is there a difference to you? There's a difference obvious to the UX writer here. So I already talked about Google Magic. Oh, skip that. We're going to skip that too, in the interest of time. Just as background, Peter and I have done this multiple times, and we have never managed to do these classes in nice 90-minute chunks. We try to accommodate, so I'm trying to catch up on time. So let's talk about virtual assistants. Okay, we all have experience with chatbots of various forms, and this is the first version of the Google Home device, which is a nice chatbot. I can say, hey, name of company, I want you to like turn on KQED or listen to NPR News or whatever, right? I just talk to it and it does the right thing. The question is, what can you say to a device like this? What's the space of possible strings that you can say to which it will respond appropriately? So if you think about it, some people will say, I can say anything I want to it, it just understands me. What that should tell you as a UX researcher is they haven't tried very many things. They really have only said a few things that they know work. And so they think of that as the entire space of all spoken communication. And that's definitely not true. If you say, hey, G, sudo, make me a sandwich, right? It's not going to work. And in particular, when you watch people actually using these AI devices, they will, for example, try to do something multiple times, and they keep trying and trying and trying, and then they can't get it to work. And maybe it's their accent. So their mental model is telling them that they know that speech recognition systems have problems with accents. And if you haven't done this, I highly recommend doing a search on YouTube for elevator Scottish accent. I'm not going to include it here because it's like 5 minutes long, but you're going to die laughing because it's about a couple of guys trying to use a voice-driven elevator like this using a Scottish accent, and it's terrifying in a funny way. But they worry about the accent because they do know their mental model about voice recognition systems is it sometimes struggles with accents. So for us as computer scientists, is this thing guided by a grammar? What would that be? First off, most people have no idea what a grammar is. And that is, Google keeps changing the recognition system so the set of things it can respond to changes positively and negatively. The negative version is called a regression. You push out an update because these things are online all the time, so we can push a new model, right? Yay! Except sometimes it goes backwards. And there are things that my Google Home device no longer recognizes that I know that it used to be able to do last month. So it's difficult to create a mental model when behavior keeps shifting underneath you. It's a little bit as though we shipped you a car. Turning right makes the thing go right. And the update comes and turning right makes it go left. Uh-oh. How do we handle that? How do we, with a mental model, how to handle it? Okay, so that's how you think of the device. How you, the user, think about the thing that you're using. What's the mental model you have of ChatGPT or Perplexity or whatever? By contrast, the user model is how the machine thinks of you. What does it know about you? Okay. So, little story here. When I first got my PhD, I went to Xerox PARC, and my first job was to build a user interface for this device. And this is a printer copier. Big, hairy, complicated. In fact, it's so complicated that they put this giant, very fancy interface on it, not this one, but the subsequent one. And we were given the task of trying to make this simple and obvious to use. Fine. So we built a whole AI system that would interface between it and you would tell it, hey, machine, I want to make 24 copies, double-sided, with plastic inserts every 5th page, blah, blah, blah. Say what it was and we'd figure out how to do it. The story here is that when we did that, we built a system that we knew would work. It was provably correct. An old-fashioned AI technique that we used to use is theorem proving. You would create a theorem about the state of the printing job, and it would then prove it, and that would then be the plan to take. So we knew it was correct. However, I was working with Lucy Suchman, who was at that time a grad student at Berkeley, and this became her PhD thesis. And chapter 6 is basically how Dan's clever AI system doesn't work. I hate to be immortalized in that way, but it's an interesting piece of work. The key idea here is alignment between what the system thinks you're doing and what you think you're doing. That is, my mental model has to be aligned with the user model of the system. And they were not always in alignment. And that was ultimately the problem. So you would say, for example, in this system, you put in a goal, I want 24 copies, blah, 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 blah. And then create the plan, it would generate the plan, and would then walk you through each step of the plan. Do this, do this, do this, do this. And we did a bunch of user studies because this was the original UI. Everybody hated this. Nobody could figure out how to make it work, right? So we replaced that with ours, which was basically that. And, well, I thought I had a picture there, I guess not. So I'll tell you what happened. We would have people come in and do user studies. And we would say to you, hey, Jack, we want you to make 24 copies, double-sided, blah, 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 blah. And then they would spend the next hour trying to figure out how to make it work. And so we had all these people come through, and almost universally they failed. Because the system thought they were in one state, the user thought they were in another state, and they couldn't reconcile the differences. And I said to Lucy, you know, we need smarter users. I don't know what the problem is here. We just need smarter people. So finally, Alan Newell and Herb Simon come in, and I said, hey, smart users, we can grab them. Herb Simon won the Nobel Prize. Alan Newell does a bunch of work in the AI, cognitive modeling and all that. Really smart people. Put them in, they fail in exactly the same way. And that's when I realized, oh, maybe it's not them, maybe it's me, maybe it's my design. And that was one of those Saul on the road to Ephesus moments when I realized I need to think about what AI is totally differently. I need to think about the human aspects of AI, and that's really where I changed my career path. Because before that time, I was a dyed-in-the-wool, hardcore AI engineer. And I realized, well, if you can't get the human to understand it, you have no hope. You have zero opportunity. So this user model, that is what the system thinks you're doing, is dependent on several things. Like what can it sense? So part of the problem with the system we built was it was terrible at sensing what the user was doing. It had a bunch of on-off switches, and that's not a great way to sense what's really going on. The reason I've got this picture here with the minivan driving through the arm is the arm device does not sense that there's a car there. Sensing failure. Doesn't matter how good your AI is, if you can't sense the world adequately, for whatever definition that is, adequately, then your AI is not going to work, right? Theorem. You also have to have a system that can interpret user behaviors. What are the people doing? What are the users doing with that AI system? What do they do with Google Search? What do they do with Google Maps? What do they do with the thermostat? We also need to have systems that track what language people use, the terms they use, and so on. Now, what we're trying to get to is a system where we have deep user models. Let me tell you, we're not there yet. This is still an open area of research. Flash, if you're looking for a final project topic, this is a good one. Just saying. Because in order to be able to align what people think is going on versus what the system think is going on, we need to sense, interpret, understand what behaviors are going on. So creating a user model means that you start to represent what the person is doing or groups of people, because sometimes your AI system has to deal with groups. And so we sometimes will, in UX research, create a persona, which is a kind of a caricature of such a person. In a system we built a few years later, we had this thing called the IDE interpreter. The only thing that's interesting here is that each of those nodes in that graph represents a piece of knowledge. It's a knowledge unit. It represents what I think you know about how to work this, in this case, a multimeter. We could do it for math skills. We could do it for car mechanics. But each one of those is an understanding. So, for example, this one here says this person has demonstrated that they know where all the parts of the multimeter are. They know where the mode switch is. They know where the red lead is, the black lead. They know all that stuff. And so this system is tracking what you, the user, know. Right? Now, fascinatingly, Khan Academy has something that looks almost identical, and it functions almost identically. So this is now 20 years later, 30 years, 30 years later. But they basically also have a knowledge network, which you might, from other courses, recognize as a knowledge graph, showing dependencies between pieces of knowledge, and they track what you, the student, have done. So, for example, look there, one of them is the concept of knowing your numbers to 100. And so what they're doing in the Khan Academy software is tracking whether or not you have demonstrated that you know those numbers. Or those, she only know the numbers up to 37. Beyond that, we don't know. So then you would say inadequate or partial representation. Point is, this is a user model that helps the system understand what to teach you next. That's a sort of a close-up to that. So, question for you, what's missing here in the user model? One thing that could be missing is the emotional state of the user. Are you happy, sad, angry, upset, irritated? If in the middle of using an AI system, you start to get really pissed off, you probably want the output of the system to change. That's what humans do. So if I see that you're getting really angry about something, and I may have nothing to do with it, you may be angry at your mom or your girlfriend or your boyfriend or whatever, right? If that changes, then I need to change. Me, the AI system, should be changing my behavior somehow. You might also want to take into account the history of the user. For example, has this user consistently misapplied a label in, say, their email tagging? Or how sophisticated they are? Do they understand what it means to reset versus restart a system? What else do you need? So one of the things that we are trying to figure out as a field is how much the system needs to understand you. So this is an example where Google Maps the other day, it pops up a little notification saying, hey, Dan, you need to check into Comfort Suites at UC Davis because you're supposed to give a talk there tomorrow. Okay, except that I canceled that reservation. The system didn't know. So this, in essence, is called the frame problem or the alignment problem, where the system thinks I'm doing X and I canceled X, but I forgot to tell my system. I forgot to cancel that event on my calendar, which is how it knows what I'm doing. See what I'm saying? We have to be aware that the system and its recommendations may or may not understand what you're doing. This is an internal Google example where alert pops up on my phone and it says, leave now, 2 hours and 11 minutes of driving time to get to Bodega Bay. But what it doesn't know is Bodega Bay is the name of a conference room in my building. I can walk there in about 30 seconds. So in this case, it thinks it knows. It thinks it knows I'm driving to Bodega Bay. And in fact, it's a syntactic mismatch. It's a type problem. I'm not going to the city, I'm going to the conference room, also named that. So when we're designing for intelligent systems, we need to take into account both the user and the mental models. I'm going to give you 2 examples, and then we'll quit for today, and we'll pick this up again on Thursday, and then we will catch up. We'll be back on speed. Okay. Here's a UI you've all seen, right? What does the little triangle mean? You see that triangle in the middle of it? Anybody know what that means? Which side the gas hole is on, right? Okay, does everybody understand that? How many people didn't know that? Yeah, a lot of people don't know that. What's interesting is that it's not in the user manual as far as I can tell. It's never explained. And so how did you learn it? Good job. How did you learn it? So you see the issue here is, what's the most salient thing on that display? Visually salient thing is that big red blob, right? Which means getting low on fuel, right? But it doesn't flash or anything. So here's another one. Customer comes in and says, I need 710. Anybody see the problem? Right? You go to Google and do a search for 710, you're not going to find anything. It's not a replaceable component in your car. But you can get 710 oil, and the gas station guy is happy to give it to you. Stand on your head. One more example here. Because when we're thinking about designing user interfaces, When we're thinking about designing AI systems, one of the characteristics of an AI system is that it's adaptable. It changes to serve what you need and provide you exactly what you need in context. It's great. So here's me using Google Docs, okay? And in the top, I just got you, I'm showing you the menu items there. And it's a whole pile of menu items. And maybe you read Egyptian hieroglyphics, you understand what all those mean. But if you, for example, then say, I want to bring up the motion menu, and you click on that and bring up the motion menu, notice what happens. Those two things are the same. Those two icons are the same between with motion and without motion. But that, where'd that go? Has this ever happened to you? Where the system is intelligent and it adapts itself to your needs in the moment, but it doesn't get it right. It sometimes will remove an icon or an option thinking that, oh, you would never need that. This is 20 minutes of me fooling around trying to figure out where that option went before I understood that when you put a new item on the far right-hand side, it rearranges the menu options dynamically and, quote, intelligently. Fundamental problem here is that the user model and the mental model are not aligned. We need to figure out how to both do that alignment and communicate that change when things shift under different uses. So I'm going to jump forward here to our question for today. This is all fun stuff, but we'll do this on Thursday. Because I want to get to this one. All right. So go ahead and answer that, if you would.